Oh, welcome back, Bernard, from the short break. Remember, we talked about the molecular arrangement in solid, liquid, and gas. But then let's take a very simple, short attention quiz. Oh, yeah. In which of the following states of matter do molecules move freely, even though there are strong intermolecular forces between the molecules? A. Plasma. B. Solid. C. Liquid. And D. Gas. Want to attempt?
Plasma.
Plasma. Mariam, what's your choice? Correction? Okay. Give her, give her. Yes.
Liquid.
Liquid. Mariam,
Gas.
gas. Why did you choose liquid?
Because it moves freely, but not like gases, and there are intermolecular forces that holds them back.
They have strong intermolecular forces, isn't it?
Yes.
And move freely.
Yes.
Mariam, why did you choose gas?
Their intermolecular forces, they move freely and they take the shape of their container, and when compressed you can
Based on the question, they move freely even though there are strong intermolecular forces between them. Is there strong intermolecular force between the gas molecules? No, only in liquids, and only liquids that move freely. You have strong intermolecular forces between molecules in solid, but solids do not move freely, isn't it? So only in liquid. Liquids, they move freely and they have strong intermolecular forces between them. But gas molecules do not have strong intermolecular forces between them. So the correct answer here is C. Okay? So we have explained energy before we went for the short break. And having done that, and previously we also have explained matter. So now, as we defined physics ab initio, that it is a science that studies matter and energy and the interaction between them, isn't it? Now we have some insight into what is matter and what is energy. And what about now matter and energy together? Are they two sides of the same coin? We have seen the different states of matter, isn't it? And we have seen some types of energy, isn't it? Correct? And we have seen that matter and energy. Remember the question I asked about, is light a matter or energy? You answered that it is an energy, isn't it? Not matter. So it is obvious from the foregoing that matter and energy are two distinct and separate entities, isn't it? Correct? But are they two sides of the same coin? Matter and energy equivalence. It turns out that in the 20th century, one of the famous scientists which I highlighted earlier, Albert Einstein, came up with the matter and energy equivalence. He realized that matter and energy are simply two sides of the same coin, that they are equivalent, meaning they are interchangeable. You can convert one from another. You can get one from another. You can get energy from matter. You can get matter from, you can get energy from matter, and you can get matter from energy. Do you understand? Hmm? Simply, this is the famous equation. Maybe you have heard of it, E equal mc squared. Okay, E is the energy, and m is the mass of the particle, and c is the speed of light squared, which is very high, 3 exponential 9 to meter per second. Okay, so with this equation, Einstein proved that matter and energy are equivalent, meaning you can get one from another. But how can we visualize this? Okay, let me put on this light. This is light, right? We're receiving the radiant energy from the fluorescent, isn't it? We're receiving energy, correct? You can see E equal mc squared. So does that mean if I can get E equals mc squared, if I can calculate the energy released from this lamp over time, so mass is equal to E over c squared, right? If I can get the energy released from the lamp, divide by square of speed of light, the mass of the fluorescent lamp will reduce over time, but by a very small amount because c squared is very large. Do you understand? The same thing with batteries. They release, energy via chemical reaction, isn't it? Over time, because they release energy, and that energy can be converted to mass. Okay, so their mass reduced by a small amount in this case. Okay, what about the giant nuclear reactor, the sun, which I explained that produces the radiant energy via nuclear fusion? The mass of the sun, as we know, you can put in like 1.3 million Earth size into the sun. It's very gigantic and it's giving us radiant energy. Does that mean the mass of the sun is also reducing? Yes? You want to answer? Yes? Does that mean the mass of the sun is equally reducing over time? Dude,
Please repeat the question.
okay. I explained that earlier that the sun produces the sunlight, isn't it? And there is no time that you wake up without, well, unless it is the sunlight is covered by clouds, the sun comes out and it produces that energy, isn't it, every day? So does that mean that the mass of the sun is also reducing in similar way that the mass of a battery or any substance producing energy will also reduce over time? Do you understand the question? So does that mean the mass of the sun reduces over time?
Yes.
Yes? Good. Why? Because it produces energy, isn't it? And it has been calculated that the mass of the sun on daily basis per second, it reduces by about 4 billion tons. 4 billion tons per second. The mass of the sun, because of the as a result of the radiation or the radiant energy that it is producing, which is converted. Because the energy over c squared can be converted, you can get the mass equivalent of that energy generated. Do you understand? Simple. This is the mass. It is shrinking. The sun is shrinking, is reducing in size. Do you understand now? Because of the energy it is producing. It is losing mass per second, about 4 trillion tons. But someone will say, does that mean over time the sun is going to be nowhere to be found? Yes, theoretically it is. But how long? The calculation was done and it will take billions of years before the mass of the sun is completely converted into energy. So it's not going to happen anytime soon. Do you understand? So this is the mass energy equivalence. There are two different distinct entities, but there are two sides of the same coin. And it takes the genius of Albert Einstein to come up with this beautiful and profound equation that connects, that explains nature, the very beginning of nature. E equal mc squared is one of the most profound equations that You see, very simple, very short. There are two equations that are like uh, that are very profound in the description of nature. E equal mc squared is one of them. There are many books written on that. And there is another one, F equal ma, the second equation of motion, which is given by Newton. Okay, F equal ma. These two equations, they are very profound. This one, E equal mc squared, describe the cosmos, the galaxies, the celestial bodies, and all that. I just use it to describe sun, isn't it? All the stars. Okay, so you can, so this came from what is called the special theory of relativity. I gave you these beautiful equations. You know, this is E equal mc squared, the key equation of special theory of relativity, postulated in 1905 by Einstein. I told you I'll be giving you some, stories, some historical perspectives. So this, when you hear about spatial theory or relativity, the first thing that comes to mind is E equal mc squared. Okay, which is also part of the extension of the Newton's laws of motion when a particle is moving at the speed of light. Because Newton's laws of motion are restricted to small speeds, the speed that are obtainable during Newton's time. But when Einstein came, he began his thought experiments, assuming an object, a particle moving at the speed of light. Mind you cannot move at the speed of light unless you are massless. So only photon travels at the speed of light. So in the last example, when I said you will be projected at the speed of light, that was just, to demonstrate how, time could change. But only a massless object can move at the speed of light. The acceleration, the energy to accelerate an object to the speed of light is infinite. So that cannot be practically obtained now. Yeah. So he now extended the Newton's laws of motion, and then later realized, introduced this relativity. As the faster you move, the slower time ticks for you. And then at the end, he came up with this beautiful equation, E equal mc squared. And then 10 years later, 1915, he came up with another one, the general theory of relativity, which extended the Newton's law of gravity as well. Okay, which gave another explanation of gravity, which we will not talk about now. Okay, so even this one is just, to connect the idea, because we are talking about matter and energy, physics, study of matter and energy. They are actually two sides of the same coin and can be, connected by this simple equation. And the examples I mentioned, the nuclear fusion, which is obtainable in the sun, and then hydrogen bomb, because sun is a big, giant hydrogen bomb. The same reaction taking place there is the same reaction taking place in hydrogen bomb, in which hydrogen is being fused into helium, reducing enormous amount of energy, of course, that destroys. And then you have cellular respiration in humans. You take in air. No, this is the breakdown. The breakdown of glucose. You take in oxygen. That's why you get the oxygen. And then glucose, which is usually the simplest form that our body use for energy production. Okay. And then these two components produce a product or products. One is carbon dioxide, which we breathe out. Okay. Two is water vapor. Okay. To know that whether you produce water vapor, just take a glass and breathe out. You will see it condensing. Or when you travel in a car and there is, it is raining, like now, and you don't put on the AC, water vapor will all stick, on the glasses. That water vapor is coming out of your breathing. On the average, you breathe out about 1 liter daily in your breath. 1 liter, human. Okay? Plants do the same thing. They breathe out water vapor through a small opening at the underside of their leaves called stomata. It's through the same process, but in their own case, they take in carbon dioxide and produce oxygen. And the product is also water and energy and oxygen. So they breathe out water, but plants can breathe out, they respire. We call it transpiration. They can transpire up to about 200 to 500 liters daily, plants. But humans, on the average, about 1 liter. Okay? And then the important component, energy, in form of ATP, adenosine triphosphate. You know, the medical guys, the biologists will now go and break it down. This is the energy that our cells will utilize, you know, and then heat. You realize, like when you are eating food, sometimes you'll be sweating, okay? So it produces heat, you know, especially we humans, okay? We regulate, our blood temperature is regulated. How? By extracting energy from our body. That is why when it's good to take cold water. Well, of course, if you are fine with that, because when you take cold water, the body will have to go and mop up, you know, extra energy compared to when it were, if it were warm water. Okay, it will mop up extra energy in order to make it to the temperature that is required inside the body. And some postulated that taking cold water 2 liters daily for 1 month could lead to weight loss of about 2 to 4 pounds. Just cold water without doing anything, because of the energy that it will be, you know, sourcing, you know, from the fats. So when it sources it from the fats, then you lose weight. Okay? So we're talking about the energy, isn't it? Okay? That we produce as a result of what? Matter. Glucose is matter, isn't it? Oxygen is matter, correct? But at the end, we produce what? Energy as a product. And this is part of like what happens also in the nuclear reaction. You take some nuclide and then they fuse into one and then energy is produced. Okay? Where it all began, that is this marriage between matter and energy. It began with the Big Bang, or the famous Big Bang theory. Yeah. Big Bang, simple, Big Bang. A long time ago, about 13.8 billion years, the whole universe was squeezed. This year is the 13.8 billion years is estimated to be the age of the universe. Are you following? So it was squeezed into one tiny, hot and dense point, which exploded. That is the Big Bang, okay? There was a Big Bang from a single point into pure energy. And this pure energy turned into tiny particles, which are the basis of protons, electrons, and neutrons, tiny particles. And these tiny particles, they come up together to form atoms, bigger atoms, stars, galaxies, and planets from this pure energy. That is where it all began, the Big Bang theory. And I think in the 60s, the first evidence of the Big Bang theory was detected, which is what is called background microwave radiation, which has been traveling for the past 13.8 billion years ago and was only detected in the 60s or so. And that confirmed the origin of the Big Bang theory. Now, this is energy changing into matter. Dude, what is it? What is it? So this is energy changing into matter, okay? Starting with the Big Bang. And from there you have the universe being birthed, okay? Coming into existence, okay? You can see from a single point, and then you see it's expanding. And the universe is continuously expanding. Since after the Big Bang, it is continuously accelerating and expanding. That is what you can see. It's expanding and accelerating. Okay? Where are we going? How is it going to end? Various theories, which we are not going to discuss. But then, there is a beautiful verse in the glorious Quran in which some clerics are of the opinion that it is talking about the Big Bang. As we know, the Quran has some scientific basis, okay? Especially, in medical sciences, to do with the conception, the fertilization of the egg and the various stages, the hydrological verses, the geological verses, the cosmic verses as well. This is one of the cosmic verses. There is a famous professor of geology by name Dr. Zaglul al-Najjar. He was a professor at Kimfad University, Petroleum and Minerals, where I did my PhD, but he left before I joined. So I did not meet him there, but he was there before I went. So he has this beautiful, explanation of the cosmic verses. And in it, he postulated that this verse, أَوَلَمْ يَرَ الَّذِينَ كَفَرُوا أَنَّ السَّمَاوَاتِ وَالْأَرْضَ كَانَتَا رَتْقًا فَفَتَقْنَاهُمَا, is referring to the Big Bang Theory. Do not those who disbelieve see that the heavens and the earth were joined together as one unit? Just look at the Big Bang Theory as one unit. Then we split them apart. Split them apart to now form the various, entities that we now have as the universe, which is explained, which is similar to what I explained as the Big Bang Theory. Okay, so this, to some clerics, is one of the cosmic verses that the Quran is clearly capturing the Big Bang Theory, the origin of all creation, the origin of the universe as it is. Well, Quran is for, to get guidance. It's not a scientific encyclopedia. Okay, so but it has some verses that have deep scientific accuracy, deep scientific accuracy. Okay, and as we move on, if I meet any of those, I will highlight it as well. Now, to units, done with matter and energy. The next thing is units, physical quantities. Okay, so we are moving gradually, okay, from simple definition, understanding matter and energy and how they are related, to units. Units are very, very important in physics, very important, to the extent that even university students, most of the first introductory courses, we teach them about units, okay, because they need to understand it. Okay, basically there are three: fundamental units, derived unit, and special unit, which you all know. There are 7 primary dimensions, okay, or 7 primary units that we all know: length, mass, time, temperature, electric current, amount of light, and amount of matter. As time proceeds, we will take each one and break it down. But for now, we will be dealing with the units, and then I'll be explaining some of these physical quantities as we proceed. Length is simply, the interval between the separation between 2 points, simple, measured by different measuring devices like ruler, tape, and all that. Okay, and then the SI unit of mass is of length is meter. It has several other units, as we are going to see. And then we have mass, whose SI unit is kilogram. Time, which is the interval between 2 events, whose SI unit is second, measured by stopwatch, clock, and all that. Temperature, SI unit Kelvin. Ampere, the unit of electric current. Amount of light, candela. Amount of matter, mole, which we normally use in chemistry. Now, these are primary dimensions or primary units. From these units, we also have derived units. As the name implies, derive, we derive the unit from other fundamental units. Okay, some consider the fundamental units to be 4. The first length, mass, time, and temperature, because like ampere, candela, ampere, Ampere and Kelvin, when you look at them, they are spatial unit. Spatial unit are termed as spatial because they represent the name of scientists that have worked, that have contributed in that area significantly. Like force, Newton. Newton, like I told you, Newton, I mean, there were a lot of other like postulates of how the universe operates and all that before him. But when he came, he finalized everything and refined, came up with the laws of motion, optics, and invented calculus, a whole branch in mathematics. So Newton almost like kickstarted the most of the fundamental basis we have in physics. Okay, so his name is assigned as the unit of force. Okay, so but when you have spatial units, they are written in capital letter. Okay, spatial unit, when you see a unit as written in uppercase, in capital letter, then it is a spatial unit, meaning it is a name of a scientist that has contributed significantly in that area. Okay, like Ampere, like Kelvin, like Newton. So all these are spatial units. And sometimes spatial units can have derived units as well. Okay, like pressure also, Pascal. Okay, Pascal, although Pascal we write as P, capital P. Let me put Pascal, capital PA, okay, which is the unit for pressure, okay, but it has a derived unit, which is Newton per square meter, okay. This is the derived unit of pressure because pressure is simply force divided by area. So how do you derive the unit? What is the unit of force? Newton? Unit of area? Meter square. Good. Meter square. So unit of pressure now, Newton per meter square. This is the derived unit of pressure. And the spatial unit is Pascal. Do you understand? So you have fundamental units, spatial unit, and derived unit. But then when doing physics calculation, you tend to have various other units, either significance of units with practical examples. Significance of units with practical examples. Like now, if I tell you this is water, oh, I drank 50 amount of water. You'll tell me 50 what? Isn't it? Is it liter? Is it centiliter? Isn't it? Is it milliliter? The volume here is 750 cl, isn't it? Centiliter, which is 0.75 liter. Correct? Now, if I tell you the length of this whiteboard is, let me say, 0.8. What question will come to your mind when I say 0.8? Unit. You will say, 0.8 what? Kilometer? Millimeter? Centimeter? Or meter? Isn't it? Because if I don't tell you the unit, the number alone, which we call the magnitude, is meaningless, isn't it? The length of the board is 0.8. That does not mean anything, correct? Unless I attach the unit to it, isn't it? When I say, oh, the length is 0.8 meter, oh, then you now have a real picture, understanding of the length, even if you don't see the board, isn't it? You can picture it because like now, like the length of this table, what do you think it should be? Just guess. Has that a wild guess? The length of this table. Maria. Approximately one meter. Hello? Has that a wild guess? Approximately? Okay. 45 centimeter. Okay, now let me get my measuring tape. This is my measuring tape. It's graduated in both in feet and meter. So let me measure it. This is 85 centimeter. So 85 centimeter, let me write it, 85 centimeter. What is it in meter? What is it in meter? 0.85. Good. 0.85 meter. So this we can say is approximately equal to 1 meter, isn't it? So 45 centimeter is far from that. You see, like now, if I'm sweating, isn't it? You can tell me, what is the temperature in this room? Say, I think the temperature is in this room is 30. What question will come to your mind? 30 what? 30 degrees, Kelvin, or Fahrenheit? All these are units of temperature. So I have to specify the unit for you to understand, to have an appreciation of what I'm trying to say, isn't it? Otherwise, my statement is as good, meaningless. And when I say, okay, the temperature I think is 30 degrees Celsius. Oh, so now you understand, isn't it? Because 30 degrees Celsius and 30 degrees Fahrenheit are two different temperature scales. 30 degree Fahrenheit is low, isn't it? When you convert it to Celsius, it will be low, isn't it? It will be lower than 30 degrees Celsius, as we are going to see, isn't it? So, units. When a car is moving very fast, how fast is that car moving? It's moving at 150. 150 what? Is it miles per hour or kilometer per hour, isn't it? Because 150 kilometer per hour is usually miles per hour is on the high side than kilometer per hour, because 1 mile is about 1.6 kilometer, isn't it? So units are very important, not only for physicists, but for everyone. For everyone. Because we talk about units in our everyday life. When we want to buy pure water, we'll ask, which one do you have? Is it 50 cl, 50 cl, or 75 cl, or even 300 ml? That is 300 ml. That's the smaller one, isn't it? So, whether you are a scientist or a non-scientist, you have some appreciation or working understanding of unit. But as a physicist or physics student, in our calculations, we have to ensure consistency in using units. We have to ensure that the units are homogeneous. The homogeneity has to be maintained in our calculations. If we are using centimeter, it has to be centimeter throughout. Or more importantly, we'll look at the SI unit, okay, which is the the international system of units. Yes. Now it takes us to the SI and imperial units. You see, you may be working in feet, isn't it? 1 foot. Then Dutch could be working in centimeter. Halum could be working with kilometer, isn't it? But now, can we add apples and mangoes? 2 apples, 2 apples. Let me use the red one. It's brighter. 2 apples plus 3 mangoes equal what? 5. 5 fruit. No, I want 5 fruit. That is a generic term. I'm talking about apples and mangoes. So is this 5 apples, mangoes, or mangoes, apples, or 5 apples or 5 mangoes? We cannot work with, we cannot add them, isn't it? Because when we add them, what is going to be the unit, isn't it? It's the unit that is the problem here, correct? But when we have 2 apples plus 3 mangoes, we simply, no, sorry, 2 apples plus 3 apples, we simply have 5 what? Apples. There is no ambiguity here, right? No ambiguity at all. So this is where you need conversion. You need to be consistent. You need to use homogeneous units. Okay? And this is why we need to learn how to convert, how to switch from one unit to another. The same physical quantity, let's take length. It has several units. Okay? And that is why in using those units, okay, there are 2 systems. Okay? The old system is the imperial unit or the USCS unit, which is the US customary systems of unit, in which you have feet, inch, pounds, and all that. Okay? And then on the other hand, you have the SI unit. The relationship between the units in the SI unit is multiple. One is a multiple of another. So it is easier to convert. It is easier to remember. Let's say, for instance, 1 foot is 0.3048 meter. This is too much. 1 mile is 1.6 kilometer. 1 foot is equal to 12 inches. So you see these numbers, memorizing them, 1 horsepower is equal to 746 watt. So this is too much. So the scientists now sat down and tried to harmonize and devise a simpler way of, writing and communicating. So they came up with the System International. It was invented by the French, I think, in the 18th century. Okay, the System International, which is the system of unit that the whole world now embraced and uses, except one country. Who can guess what that country is? The industrialized nations, except one industrialized nation, the United States. It is still using the US customary system of units, the imperial units. Of course, it has, included few of the SI units, few like ml, it is using ml, centimeter sometimes, but basically it is using the imperial units. But all other countries, industrialized nations, are using the SI units, usually in teaching, academic, and all that. But then in practical engineering, let me put it this way, in practical measurement, we normally use the imperial units. If you want to go and buy a plot of land, they will not give you the area in meter square. They will give you the area in feet. They will say 1 full plot, they will say is 50 by 100. What is the unit? Feet. 50 by 100 feet or feet square. That's the area. 50 feet by 100 feet. Okay. When you want to buy a pump, they won't ask you the kilowatt. They will ask you what is the horsepower. 1 horsepower. When you want to buy a pipe, they will ask you how many inches. 3/4 inch, half inch. All these are the US customary units. So in practical engineering, up till now, we mostly use the US customary system of unit. So that's why it's good to understand both systems. But for academic purpose, for solving problems, we will usually stick to the SI unit. Okay? So that is why when you have a problem, it's good to convert everything to SI units before solving. If any of the physical units is not in SI, then you convert it to SI unit. Okay? That makes the whole calculation easier. Okay? Just like I was saying, 2 apples plus 3 mangoes is, imagine in your calculation you have feet, you have millimeter. Then you all convert them to meter, which is the SI unit of distance, isn't it? Okay, and this is so you can see these are the various physical units that we have: acceleration due to gravity, area, depth, diameter, length. You know, their corresponding SI units and imperial units. Okay, shear stress, surface tension, unit flow rate, velocity, viscosity, weight, and all that. Okay, so now I will send you the slide. Conversion of units. Okay, we move to the conversion of units. You must be familiar converting units from centimeter, millimeter, kilometer to meter. Yes, I think. Let me put on the line. Oh, this one is. Oh, okay. Because I will use the board. So you must be familiar converting units from one length, centimeter, millimeter, kilometer to meter. Okay. So like I told, all these are form of the SI unit of length is meter, but others are related, you know, with exponential. Okay. Like how many centimeter gives 1 meter? How many centimeter gives 1 meter? 100 centimeter is equal to 1 meter, isn't it? Madam, how many kilometer equals 1 meter? 1000 kilometer is equal to 1 meter. Huh? Simply 1 over 1000, isn't it? Correct? Because 1000 meter is equal to 1 kilometer, right? And then, so 1000 meter is equal to 1 kilometer, right? Uh, 10 millimeter, no, not 10 millimeter. 100 centimeter is equal to 1 meter, correct? And 1000 millimeter is equal to 1 meter, right? And 10 millimeter is equal to 1 centimeter, correct? So now, how do we convert from one to another? Because the most important thing is to know how to convert to the imperial unit, okay? To know how to, to the SI unit, which is meter, okay? And also, 1 foot is equal to 0.3048 meter, okay? Foot, of course, is imperial unit, okay? So now, imagine I have 10 kilometer. What will it be in meter? Okay, so the simple way to do conversion, okay, is what we call by cross multiplication. Okay, so you quote the relationship first. Okay, now 1000, 1 kilometer from this relationship, isn't it, is equal to 1000 meter, correct? So what about 10 kilometer? It's going to be equal to x, isn't it? Then we cross multiply, right? Okay, this times this is equal to this times this, isn't it? Okay, so 1 times x is equal to 10 times 1000, right? So x, which is in meter, isn't it, is going to be 10,000 meters, right? Meaning 10 kilometer is equal to 10,000 meters. Of course, you can just look at it and say, oh, by this 1 kilometer equal 1000, then 10 is just okay. But this is like the mathematical way, because sometimes you may get confused, and so in case you do that, you can follow this long method. Okay, and of course, if you have foot and all that, all you need is to remember the basic connection, okay, between the units. Okay, if I say, this length, the length of this is 190 centimeter. So 190 centimeter, what is it in meter? 190 centimeter, what is it in meter? 1.9, because you divide by 100, isn't it? 100 centimeter is equal to 1 meter. So when converting from centimeter to meter, you divide, okay? And from meter to centimeter, you multiply. Simple. Do you understand? Unit conversion is very important, okay? Now, this is about length. So if you have a calculation in which you have these units combined that are not in meter, you have to switch them back to their meter equivalent. That's the most important thing, okay? Before you do your calculation, okay? Because you cannot combine mangoes with apples. Now, the next one is mass. You have some units, gram, milligram to kilogram, okay? And what are the connections, okay? 1,000 grams is equal to what? Alum. 1,000 grams is equal to what? 1 kilogram, okay? And of course, milligram, that's 10 to the power minus 3 of a gram, isn't it? Okay, 1 gram is equal to 1,000 milligram, isn't it? Because milli is a prefix, okay? Milli means exponential minus 3. You are dividing by 1,000, okay? And from here you can switch to kilogram, okay? Of course, when you're dealing with smaller units in practical terms, you measure in grams. When you are using with larger units, let's say you want to measure your weight, okay? What is your weight? Dude, what is your weight? Like my weight, maybe now, I think 72 kilograms, okay? If I will measure it in grams, my weight is 72 kilograms. So what will it going to be in grams? It's going to be, what will it be in grams? 72,000 grams. You multiply by 1,000. 72,000 grams, because you multiply by 1,000, correct? But normally, in calculation, we usually switch them to the SI unit, which is the kilogram. So the kilogram can be small, but in practical usage, when the amount is small, you use grams. When it is large, you use kilogram. If it is very big again, or large, or heavy, you use tons. Okay? Ton. Because one ton is 1,000 kilogram. Okay? Like in the case of the mass of the cars, okay, we use ton. Okay, 2 ton, 3 ton. Okay? So, and vice versa, like I said, but for calculations, we normally calculate the SI unit, but we need to learn how to switch to other non-SI units, or others like kilogram to milligram, depending on what we are dealing with. But for most cases, we switch to the SI units, okay? But for practical cases, we may have to switch from the SI unit to the non-SI unit, okay? The next one is temperature. It has several units, but four. You have Rankine, you have Kelvin, you have degree Celsius, degree Fahrenheit. Here we normally, in weather forecast or in your phone, when you open it, you will see, okay, what is the temperature like today? Okay, the forecasted temperature. Is it 30 degrees Celsius, Fahrenheit, or Kelvin? Okay, normally we use Celsius here. The US normally use Fahrenheit. Okay, so you may find yourself trying to switch, but the SI unit of temperature for calculation purpose is Kelvin. Okay, for practical purpose, okay, knowing the temperature, the weather, and all that is, being forecasted using degrees Celsius or Fahrenheit. But the SI unit is Kelvin. So when switching from degrees Celsius to Kelvin, you add 273. Okay, let's say the temp. Let, let's say the temperature today, let's say 30 degrees Celsius. Okay, so what is it in Kelvin? Okay, okay, and that gives what? 273 plus 30? 303. So it gives 303 Kelvin. Kelvin, you don't add degree. It's not degree Kelvin. Very important. It's not degree Kelvin. All others, they have degree except Kelvin. Degree Fahrenheit, degree Celsius. Okay, but Kelvin has no degree. Okay, now what about switching from Fahrenheit to Celsius? In that case, we use this formula. Okay, this is the formula from Celsius to Fahrenheit. Okay, degree Fahrenheit is equal to 9 by 5 times degree Kelvin plus 32. And you can also derive when you want to switch from Fahrenheit to Kelvin, sorry, from Fahrenheit to Celsius by making the degree Celsius the subject of the formula. Let me give you an example. Okay, this is Kelvin. Okay, now what will be this? The same 30 degrees in Fahrenheit. Okay, in Fahrenheit. What is the value? 30 degrees in Fahrenheit, in degree Fahrenheit. Okay, you just put in the formula here, isn't it? Which is 30. What is it? Times 1.8 plus 32. 30 times 1.8 plus 32. What do you have? What? 86. Okay, you see, this is 86 Fahrenheit. Okay, now what about if I want to get the formula that will give me degrees Celsius from Fahrenheit? Make degrees Celsius the subject of the formula. Change of subject in mathematics, isn't it? So what do you have? Work it out. My degree Celsius, what is it going to be when you make it the subject of the formula? Done? Done? Hello? What do you have? Marioma, what do you have? Make degree Celsius the subject of the formula from here. Change of subject. Done, done? Or will that be the first assignment? No, it will not be. Done? Okay, let's do it together. This is it, right? We take 32 to the other side, isn't it? So we have degree Fahrenheit minus 32, right? Is equal to 9 over 5 times degree Celsius, correct? Next, we have to take this 9 over 5 to the other side, isn't it? We are dividing. When it goes to the other side, it will flip, correct? It becomes 5 over 9 because we multiply and divide by 9, isn't it? So degree Celsius is now equal to 5 over 9 into what? into degree Fahrenheit minus 32. Correct? Isn't it? So that is how to calculate it. This is now the formula for degree Celsius. Okay? Degree Fahrenheit minus 32, multiply everything by 5/9. Okay? So now, what did you get before? Concluding remarks, summary. For our first lesson today, we have defined physics, isn't it? Explain what is matter, the states of matter, the arrangement of molecules in the different states, okay? Explain energy with examples, conversion of energy, and how matter and energy became the two sides of the same coin, okay? We went into units, defined the different types of units, and some simple conversions here and there, isn't it? Now, Q&A, questions. Any question? From what we did so far? Don't worry, at the end there will be assignment, definitely. So, if there is anything that is not clear, especially the basic ideas that we elaborated. Any question? Yes? Yep.
You need mention of ionize.
Ionize. Okay. In chemistry, okay, like when you knock off electron from an atom, it becomes ionized, isn't it? Because ordinarily it is neutral. Let's take, for instance, let me give you example of let's say oxygen, the oxygen atom. Okay, the oxygen atom has how many electrons? Oxygen O16, isn't it? 16. And then atomic number, atomic weight, what is it? Yeah, oxygen. 16, isn't it? It's number 16, correct? So atomic number and that's atomic number 16, isn't it? So what happens when you knock off an electron? It becomes short by one, isn't it? It becomes short by one electron. And electron is, what is the charge on electron? Is it positive or negative? And is it positive or negative? No. Electron is negatively charged. Electron is negatively charged. Okay? It is proton that is positive and neutron that is neutral, right? And the number of electrons have to be equal to the number of protons for an atom to be electrically neutral, isn't it? So when you knock off an electron, the atom it has lost one electron, isn't it? So it is not electrically neutral. The number of positive protons are greater than the number of negative electrons. So it becomes effectively what? Positive. Because the positive is higher. So it becomes charged. That charge that you write on top, positive or negative, okay? O2, okay? Maybe it's higher by 2 electrons, or like sodium, ion. This positive, negative, okay? These are ions. They are charged. So this is what is ionized. Okay, when you gain or lose an electron or proton, as the case may be. Okay, but without these charges, then it is neutral. It is electrically neutral when you have equal number of protons and electrons. So this is more of chemistry than physics, but that is ionized. When we say it is ionized, it means that it is charged. Okay, the gases are charged, and when they are charged, that's why you have the spark in lightning. That's why we say lightning is a plasma, because you have a spark, because the water vapor molecules, some of them became charged, and then due to what is happening in the cloud, you have electrical movement going on, and then you see the light. Okay, and of course in the something, the sun is what is happening. Okay, hydrogen fusing via nuclear fusion, smaller atoms of hydrogen fusing together to form helium nucleus, releasing huge amount of energy, and that is what is called nuclear reaction or nuclear fusion. In this case, nuclear reaction is simply, a nucleus either splitting to smaller ones or fusing with others to form larger ones, but in each cases releasing enormous amount of energy. Clear? Don't worry, we'll go into there's nuclear physics. Any other question? No question? All right. Okay. Hello.
How many galaxies are present?
Galaxies. Over 2 trillion galaxies so far. 2 trillion. So the world, the universe is a very, you know, big something on a large scale that you cannot sometimes imagine. Imagine us sitting here, you know, listening to this lecture while the earth is moving very fast. Do you know the speed of the earth moving around the sun? Can you imagine? 30 kilometers per second. The earth is moving as I speak with you at the speed of 30 kilometers in 1 second around the sun. And you have no idea that the earth is even moving, let's say, 1 millimeter per second. But then the sun is pulling the earth at the speed of about 230 kilometers per second. Because the sun is moving, isn't it? It's moving while the earth is rotating, isn't it? The sun is moving at 230 kilometers per second along the center of the Milky Way galaxy. And the Milky Way galaxy is moving with all the other stars, about 400 billion of them, around the center of the universe at the speed of about 580 kilometers per second. Now, what is your speed as you are sitting down there? Let's see. Let's work out what your speed will be. 30 coming from the earth, isn't it? 230 coming from the sun, pulling us, isn't it? Around 580 coming from the Milky Way galaxy, pulling the sun with it. So, what do you have? 840 kilometers per second in 1 second. That is your speed as you are seated right there. And you have no idea that what we call the earth is even in motion. We are even having this kind of huge, incredible velocity. Now, the moon rotates around the earth at 1 kilometer per second. Now, what will be the velocity of someone on the moon?
Around what?
The moon moves around the earth at 1 kilometer per second. So, what will be the velocity of someone that has landed on the moon? You on earth is 840. Someone on the moon will be what? 8:41. Someone on the moon will be moving at 841 kilometer per second. 841. Because the earth is pulling the moon at 1 kilometer per second. And then the sun pulling the earth at 230, and then the Milky Way galaxy pulling the sun at 580. All these incredible, velocities, you don't feel anything. You feel as if the earth is even static, isn't it? So when you are seated down one time, just imagine all this incredible velocity. 840 kilometers in 1 second. 840 kilometers is like from here to Lagos. From here to Lagos is around 800 kilometers. Moving from here to Lagos in 1 second. Can you imagine that? From here to Lagos. Well, you haven't been to Lagos, but at least you know that it's very far, isn't it? It's very far. From here to Lagos in 1 second. That is your speed. And you have no idea. So, see you in lesson 2, where we'll be looking at mass and weight. Yeah, there will be assignment. Oh, you have a question? You see here, if you look at it, I'm trying to connect physics with the cosmos, isn't it? The universe, the stars, okay? And all that. And all the other physical and practical examples. Because that way, you will appreciate the little things, the small things that will be taught. Okay? When we mention velocity, this amount, okay? Yes? Dude.
Why is the first letter of Newton mentioned in pressure?
What? Why is the first letter of Newton mentioned
In the pressure.
in what?
In pressure.
In pressure? Because pressure is force over area, and Newton is the unit of force. Okay, so that is why it's Newton per meter square. Newton as the unit of force. Okay, because pressure is force divided by area. Clear? Any other question? Arioma, you mentioned that you have several questions. Yeah, hello.
Why is it the unit of force?
What?
Why is it the unit of force?
Why is Newton the unit of force? Because Newton gave us the laws of motion. And in the laws of motion, there are so many mention of force. Okay, the first law of motion, the second law of motion. That is where we got the famous F equal ma, which I told you, this is one of the most important laws of nature. E equal mc squared and F equal ma. Okay, so Newton made a lot of effort in identifying forces, gravitational force as well. Okay, he discovered gravity. We'll discuss about gravity shortly as well. He discovered gravity. Okay, so that is why, because of his enormous contribution in force and its expansion and its explanation, its understanding and all that, so his name is attributed, is given as the name, as the unit of force. Of course, he did a lot of other things. Like I said, he discovered calculus, an idea, okay, a whole branch of mathematics. Okay, and then he discovered optics. He discovered, I told you, light has white light has 7 colors. It was Newton that discovered it as well. He constructed the first reflecting telescope. He's the greatest astronomer that ever lived, Newton. Since his time, he calculated the period, the motion of the moons of Jupiter around Jupiter using calculus. Okay, so he did a lot of things, a whole lot. But as we proceed, we will be highlighting some of those things that he did in physics. Yes. You have question? Question? Any other question? No question? All right. I think it's time we call it a day for today, and then we watch out for lesson 2. Like I said, where we'll be looking at mass and weight, types of motion, types of forces, probably move into friction, and then move into velocity, acceleration, and all that. Okay? Thank you.